So I tried this probably, this is like number 3 or 4, as far as trying to make the next part of the turbine flow video. And I was actually writing out like a script for it. And while writing out the script for it, I had a question, asked AI a question. AI told me I was wrong, and I argued with it. It showed me how I was wrong, and now we're here. Why it's taking so long. Also, very busy. Lately it's been like 2 to 3 turbochargers a day, along with fabrication, repair, and custom mods to turbochargers, piping, fixing things. It never ends. Uh, I don't know if that's coming up on audio, but that's a local truck I did a turbocharger for, and that's how it gets driven every day. It's pretty good. It does burnouts and does that. Completely clean truck. Runs fantastic. Really cool to kind of build something that lives in all, like the next harshest environment next to the motor and transmission, and have to like listen to it driven hard every single day. And know that the tools I've bought and the time spent studying to assemble these things properly is functioning. I don't know if there's like a right or like a, I mean, there is a right or a wrong, but the degree to which it's done is satisfactory enough to where you can beat the crap out of it every day and it survives. I think this works. I'm going to face everything towards me, and then I'm going to invert the video after I'm done with it. Yeah, that's nice. Okay. So we have a bunch of compressor maps. We've gone over compressor maps. I've shown you how to find out where you're on the compressor map. It's really easy because the turbocharger doesn't care what this is, right? Turbocharger doesn't care. Um, sorry, the engine doesn't care like what the turbocharger is. So this is a 60 or a HX50 or 60, 476, 48, 4. I think it's an S362, SX3, 72, GT40, 88. So engine doesn't care what this is. All the motor knows. Where's a Where's the thing to block this? This is probably too heavy. All the motor knows is the pressure ratio the engine's running at, and what that equates to as far as the landing zone. So it's the pressure ratio times the weight of the air, which is temperature based. That'll jack up the density, the weight of the air per 1 cubic foot, and then you just need to know how much air the engine's consuming per 1 cubic foot. So, like I said, this is a really easy one: 5.9 liter engine at 2,000 RPM, engine speed at I think 80% volumetric VE is 166-ish CFM. So and if it's, say, your post intercooler temp is 100 degrees, it's and you're at a 2.0 pressure ratio, it's 2 times 0.07, and then you take that and multiply by 166. So now you have, the pressure ratio at if this is for engine flow, this isn't for turbocharger flow, right? If you want to like really be a stickler, you can be like, well, there's a pressure drop across the intercooler, and there might be a pressure drop at the inlet of the turbocharger. You got to go check all that stuff. Fine and dandy if you're troubleshooting. This is just learning how to do this. So you just go 2, and then you do that, and you come over, and it comes out to like, I'm pretty sure it comes out to like 24 pounds or something. So you go 2, 24, you're right here. If you want to look at like an efficiency line, it's somewhere around 65%. So that's where that lands. Right? It's pretty easy. And why it's easy is because the inlet condition to a turbocharger is pretty much 14.7 PSIA. So we have this inlet condition, and the amount that this inlet condition can vary, let's just say we have a restrictor on it, is going to be 4.7 times 0.528. So I want to say this comes out to 9 or something. My phone is my calculator, so and I didn't pre-record this, but whatever this drop is, if you can get there, which is it's not like a big number, but it's actually relatively ridiculous to actually even get here. For an example, most carburetors, as far as the flow rate of a carburetor, is set at a 5 psi drop inside the carb's throat channel. And although a 5 psi drop inside the carb's float channel doesn't seem like a lot, um, maybe I'll throw it in right here. I have an absolute pressure gauge. We'll go to a vacuum cleaner, which we all know how fast the air goes through the vacuum cleaner when you start to block it. The airspeed goes, to our opinion, ludicrous level. That's like 1 psi of pressure drop. And the carb's tested here. So air moves extremely fast with very small changes in pressure. So what that equates to here is it's actually pretty hard to get like enough pressure drop for you to actually net this unless your air filter's too small or the ducting to the charger's too small. So if the charger's not ducted at all, usually what happens is the actual airspeed through the blade channels gets too high. So you have airspeed limits, just like you have an airspeed limit at the inlet of the charger, you have an airspeed limit across here. What can happen is the airspeed limits through here will reach a point where they're too fast. And that's what you're seeing here is the airspeed limit is becoming a problem. So the turbine has to increase in speed quite a bit, right? If you look at this speed line, if you were to run your engine's boost circuit based off of charger speed, you'd end up with a falling boost curve if you were to target a certain speed and you were able to use like the entire map. So you can see as like from this area it remains pretty constant, and as we carry the engine's consumption rate, the charger has to rotate at an exponentially faster rate as we keep carrying out this way. Turbine housings work on the flip side of that. So how these things work is when you're pulling air through an orifice, the max speed you can reach that orifice is what we went over. It's 14. It's whatever. It's atmospheric pressure divided or multiplied by 0.528, and then that is your atmospheric pressure at which the gas velocity is your local speed of sound. The opposite happens here, where you take your pressure in the downpipe. If you said you had 1 psig, you would take, or actually, sorry, yeah, that's 1. You would take 15.7 divided by 0.528, and then minus 14.7. And at this pressure, gauge now, because we took the atmosphere back out of it, that's your drive pressure. When your drive pressure hits this number, and then your downpipe pressure is at that number, the flow is choked. So your flow is choked right here. The definition of this is what makes, I think, most of the misinformation the problem, because although choked flow on the compressor side means that the compressor can no longer move more gas than it currently is, choke flow on a turbine side does not. What choke flow on the turbine side means is that the velocity through the nozzle, I even have one, sure. The velocity through here, your nozzle, or velocity through your turbine channel, because this is an individual nozzle. So just like 2-valve and 4 valves, how the ports work, it's the same deal. So right here, what it means is that the velocity through each channel, because you view each one of these as an individual CSA, cross-sectional area, is the local speed of sound. So now what you do to flow more once you're at this state is you raise the temperature or you raise the pressure. Now, so choked flow means velocity, so the speed at which the gas can transfer from one tank to another. So our first tank's the pre-turbine and our second tank is post-turbine. Velocity of the gas the local speed of sound. So how do you flow more? Actually, real quick. So what this means is you don't have to, once you are here, you don't have to calculate the velocity of the gas, because all you go and do is look up what the speed of sound is at the temperature and pressure you're at, and then that's your input into the mathematics, right? You don't have to go, my nozzle's this CSA, the turbine's this CSA, I got this temperature, pressure. You don't got to go do all that stuff that you normally do when you're not at the choke flow limit yet. And then when you are at the choke flow limit when you are at the choke flow limit, all you do is just go look this up. And that's what your input is. So, for those of us that are, not us, for those watching that are smart, you see where I'm going. For those that are pretty much like me, we're going to keep this rolling. So how do we increase the mass flow? If for reference, if you have 1 psi in the exhaust and you want to do this, it's 1.89. 1.9 is the choked location. Well, if we know that the velocity is the speed of sound, you just raise the temperature or you raise the pressure. Temperature, pressure. So as you raise pressure, your ROI on increase in velocity isn't as good as raising the temperature. Increasing the temperature increases the speed of sound quite a bit versus pressure. Now they both do it, and that's how these things function. This is an active system. That's why you can continue to increase the mass. And now that as far as why turbine housings keep flowing more gas even though they're in the state of choke flow, right? If we look at pretty much every single factory diesel that's from like at least 89 to current, they all run well over in here. Right? They operate like you see it online a lot where people are like, the turbine is choking up. It's choked out. or whatever you want to, whatever text they put on the forums. And the truth is that the turbine housing or the turbine side is in a state of choke flow. If you have a free flowing exhaust, as soon as you pass here, you're gonna say a choke flow. And I'm pretty sure, what's that? 2018. It's like 18 or 21 psi pounds of psi drive pressure. So if you look at any turbo diesel, pretty much every single one of them is in this state because they all run more than 20 psi gauge of drive pressure. So like, how does the motor continue to rev up and the choke flow doesn't get any, like, doesn't scale significantly worse? It's because the temperature rises and the pressure rises, and as those two things increase, the amount of mass that can be passed through the turbine housing and wheel set per moment given a time is still increasing as long as those two are increasing with it. So I think we'll probably do, this will be part 1 right there, and then part 2 will be why these look different and yet what, they're the same thing. It's actually a really good sheet here. This is if you convert the speed lines over on a compressor map, they look pretty much just like this. So this will be part 2. And part 2, actually, I'll pause.